We're now coming to the big idea for dealing with large matrices, and that's Krylov subspaces. It's a big subject, and it's going to take us some time to get all the way through it. So let's just get started and realize that we're going to be pursuing this for a while now. So let's first start with an observation. So remember, with the power iteration, we find this sequence of vectors. Each new vector is gotten by multiplying the previous one by a, and then dividing by some constant. So that means that the vector xk that we come up with in the power iteration is some multiple of a to the k times the starting vector x0. Okay, so one way of thinking about that, just putting different linear algebra language on it, is that this vector xk lies in the subspace spanned by this one vector. So I'll remind you of the span of a set of vectors. It's just the set of all linear combinations. So the set of all C1v1 plus C2v2, etc. such that these numbers are real or complex depending on the context. And we're going to use a special notation for this. We're going to write this as angle brackets around those vectors. So the span of a single vector, to get back to the specific case here, the span of the vector x superscript k is just the set of all c times xk. That is a one-dimensional subspace. Now, if we're going to be looking for an eigenvector in this subspace, right, there's not much of a choice, because remember, eigenvectors are only determined up to constant multiples anyway. And so really, there's only one choice. I mean, it doesn't matter how we normalize the vector. So it's just any representation of the basis of this space is the only choice we really have. And so the fact that we're looking in a one-dimensional space really limits the options. So there's a very simple idea to improve on that. So we had all these previous iterations that we're not using directly. They just helped us get to the place that we are. But we could use them more thoroughly. So we had to create all these vectors on the way to getting here, right? So these are from previous iterations. So why not use them? So why not take the span of those vectors? Well, this is what we call a Krylov subspace. It's one that's the span of vectors that are all multiples of a to some power times some starting vector. We'll set up the notation and the definitions in a second, but we'll just point out that things can only get better. If before we looked only in this dimension of the space, and now we're allowing ourselves to look in all the other dimensions as well at the same time, well, we can only do better by doing that. And it turns out we do a lot better. So let's now shift our notation away from power iteration so much and talk a little bit more abstractly. So we'll now define this matrix capital K sub m. Okay, it actually depends on the matrix A and the starting vector u. And we'll call this the Krylov Matrix. So it's n by m. We're saying A is a n by n matrix. So it's a little unfortunate, but it is consistent with the way we've been doing things. It's n by m, where n is greater than or equal to m now. So we're only going to do this up to the nth power of A. Now, here are some facts about these Krylov spaces. I didn't define the space yet. So the Krylov space, or the Krylov subspace, is defined as the span of those same vectors. Okay, in other words, it's the column space of the Krylov matrix. This is another way of putting it. Let me just fix this here. Okay. And for this notation, we'll use a curly K. So the curly K means the space, the regular K means the matrix. Okay, so some basic facts about these subspaces. They are nested. So what that means is that as a space, K1 is a subset of K2, which is a subset of K3, and so on, forever. They build on each other. So if you think in terms of span, right, from the standpoint of K3, K1 is the Krylov space where we would take C1 times U plus 0 times AU plus 0 times A squared U. So that's certainly, every element of K1 is also an element of K3. But then there are elements of K3 that aren't in K1. So it's this growing nested sequence of spaces. We can construct these spaces by just repeatedly applying A to a vector. So again, we don't actually take the powers of A, we apply A repeatedly to previous vectors from the sequence. And that way we avoid taking a power of a matrix which destroys the sparsity. So all we ever have to do is A times a vector to build these spaces. Next fact, if X is in the Krylov space Km, fancy Km, then X equals the matrix Km times Z for some vector Z. So again, this is just a question of definitions. If X is in the Krylov space Km, that means that X is equal to Z1U plus Z2AU, and so on. That's by definition of Km. But then we know that a linear combination of vectors is the same as a matrix times the column vector, which is the reason we picked our definition of the Krylov matrix Km in the first place. So that's just the same trick we've been doing with matrix vector multiplication since pretty much day one. Okay, and then finally, if A is a non-singular matrix, then the dimension of the mth Krylov space is exactly m. Okay. So the big idea that we're going to be working with, okay, is we have this big matrix A that operates over a huge dimensional space, Rn. What we're going to do is we're going to approximate this by something which is lower dimensional that we can handle. And the lower dimensional space that we're choosing is the space Km. So there's a number of questions that we're going to have to ask about what this big idea means. So why is it a good idea? How does it work in practice? But the first question we really have to ask is, how does this work? How do we do this? What does it even mean to replace the action of A over a whole space with its action over a smaller space? And really, it's up to us to decide how to do that and then see if something useful comes out of the idea. So here's our very first answer, which turns out to be not the right answer, but it will take us to the right answer eventually. So the first answer is to consider, of our two problems, linear systems and eigenvalues, it's a little easier to talk about for linear systems. So let's say we're solving a square system ax equals b. Okay, the full problem, right, we could rewrite this as b minus ax equals 0. And we'll just assume that a is non-singular, so it has a solution. All right, so if it has a solution, of course, we could recast this as a minimization problem. The smallest that the norm of b minus ax could ever get is 0, and so if we minimize it, we get the solution, right? So the solution of this minimization problem is the same as the solution of the original. It's x equals a inverse b. Okay, but that allows us to replace it with an approximation problem, or an approximation of the original problem. So instead of minimizing over all of Rn or Cn, if it's complex, we're going to minimize it over a much smaller space. Now, we're no longer necessarily going to get the answer. We would only get the answer if x happened to lie in the space where we're looking, if the true x lied there. But hopefully the x that does satisfy this minimization will be close to the true x. Okay, but let's not even worry about that part of it yet. Let's just see how this would work. So, of course, if x is in the Krylov space Km, it's equivalent to x equaling the Krylov matrix Km times the vector z. So we'll plug that in to our minimization problem. So now we're looking over all possible vectors z, which are m-dimensional. And we're going to minimize b minus a times x, but x has this form, kmz. And then, of course, we could rewrite this as a minimization over z of b minus the matrix a km times z. And this is just an ordinary linear least squares problem. Which is sort of motivates why we look at it, because we know how to solve it. Okay. So we know how to solve linear least squares problems. We know how to do all of these things that we're doing here, so let's see how it works. Here's a numerical experiment. A is just a random 50 by 50 matrix. I don't care that it isn't sparse in this case. We're just testing out the idea. And B is just some arbitrarily picked right-hand side. So it's common when you solve ax equals b to use b as the vector u. Remember the Krylov matrix, right? Where'd it go? The Krylov matrix is seeded by this vector u, and then depends on the matrix A as well. So what we're saying is for u, we're going to use the vector b because we have that vector lying around in our problem. Okay, so at first that one column is the whole Krylov matrix. So we solve the linear least squares problem. Using a backslash. Okay, once we have z, we can reconstruct the x, okay, by k times z. That was our definition of x. So this is our approximate solution. So that's an x that lies in the Krylov space. And then we'll see how good a solution it is. So we're just going to take the difference between b minus ax. That's what we call the residual. So this is our quality measure. And then we're going to add a new column onto the Krylov matrix, which is a times the last column. Again, if you look at the definition of the Krylov matrix, one column is just A times the previous column. Okay. So this is the next column of the Krylov matrix. So we run this code. Let's not worry about these warnings for a second, but they are important. Let's just see what the results are. So if we look at the residuals, you see that for a while, they decrease nicely. That's what we want, right? We're trying to drive this residual to zero, ideally, or at least small enough to make us happy. So for a while, we're getting happier. But then we see they get worse. The residuals get larger. And that's not good news for us because it means we're getting further away from the solution rather than closer. Well, there's a simple explanation, and it is tied to those warnings that we were getting. So, again, think back to the power iteration. We do know that a to the m times u converges to a multiple of the dominant eigenvector. So that means that in the limit, as m keeps growing, the columns that we're putting into this matrix are getting closer and closer to parallel vectors. Well, that's kind of the opposite of what we really want. Remember, our ideal for numerical work is a matrix that has an orthogonal set of columns, or even better, orthonormal set. Right? Those are the ones that avoid cancellation errors. If we have nearly parallel vectors, that's exactly the situation where you could add two of them together and get something incredibly small, which creates loss of significant digits. And that's effectively what happens. The way it's manifested is in the linear algebra sense is rank, or as we now know, the singular values of the matrix. So, of course, a low rank matrix has columns which are linearly dependent. One way of two vectors being linearly dependent is for them to be parallel. And so as we get larger and larger, we just keep adding vectors that look more and more parallel, and so the rank should be growing, right? It should be increasing by 1. Mathematically, they do, but numerically, they don't. They're so close to being linearly dependent that the machine can't tell them apart. And so our first order of business is going to have to be to fix this aspect of the problem. So we know we like certain aspects of these Krylov spaces. The fact that they're nested, that we can construct them by repeated application of the matrix, and so on. But they do not make a suitable numerical set of vectors for us to work with. So we're going to have to replace them with something better.